Hello, this is Matthew Preston. I'm going to be talking about my final presentation for Georgia Tech Practicum class for the Masters in Cybersecurity. My project is lowering avionics bus trust for the ARINC429 bus and trying to move it towards zero trust. So I'm going to be going over the problem, solution, a demonstration, evaluation, metrics, limitations of my solution, and then future work that can be done on this project. So the problem is pretty simple. ARINC429 bus architecture is inherently insecure, so any command that is sent on the bus is trusted and executed by receiver LRUs as long as it is applicable to that line of repulsive unit and the integrity parity bit on the end of that word is correct for the odd or even amount of ones in that word. So this can lead to compromising legacy systems where software is pretty old, and as well as the bus architecture itself is pretty old, can be kinetically catastrophic for military and civilian aircraft. So going over to the CIA triad on the ARINC bus, does it have availability? Yes, it's very robust and available. It's weather tested in many situations. Does it have integrity? Well, there's only really that parity bit that checks for integrity. So if you mess with the word in the middle of transmission and keep that parity bit correct for the odd or even number of ones in that word, it'll still be received and not dropped by any LRUs. And then confidentiality, if you get on the bus, well, every receiver on the bus necessarily hears every command sent on the bus, so there is no confidentiality. So for the attack narrative, let's say that you're a person of interest on a civilian airline, you've been critical of a government, and you have sought asylum in another country living away from that government, and that government wants you back to arrest you and persecute you under their laws. So this flight I just found on July 2nd goes from Germany to India and passes over Iran, so we'll be taking Iran as that government, trying to force a plane to land basically within their airspace. So I will be emulating the effects of the Qantas Flight 72. Now, that was not a cyber attack if you read the official report by the Australian government, but what happened there was the plane didn't necessarily crash, but since the plane dipped twice because there was a problem with the ARINC, the first officer had to declare a mayday and then they landed. So what if you could do this on command and force a plane to land in your airspace on one of your airports? Then you could go aboard and arrest that person of interest and apprehend them and then do what you wish with them. So the pseudocode idea for this attack is not terribly complicated. Basically, if your latitude and longitude are within the selected airspace, then you send 100 dive words and then force that plane to dive, and then they declare mayday and have to land within your country. So my solution was creating an ARINC429 simulator and simulate the LRUs. This is from the ground up. And then I created an attack proof of concept, and then I created an intrusion defense system against that attack, and you'll see a snapshot of the code there where that's the function that actually alerts or logs on words, and then an example of the rules section there. So before I head into my demo, I do want to talk about my process a little bit. I went from the spec sheet to creating bits, the voltages on the wire, and then simulating those into full words. From there, I can simulate LRUs that send and receive specific words, fit those LRUs together with the bus architecture into my simplified model, create an attack, and then an IDS. So heading over to my demonstration, I'll first start with my mega test code base and show you the functions that run from the ground up. And you can see it's creating a high and low speed bits for ones and zeros, stringing them together into random words, and then specific words. And then for my main function, this is taking in all the threads for all the LRUs in my model, and it will be sending and receiving, excuse me, that's the test again. It will be sending and receiving words on the bus. And so it just takes a second to boot up. And this is slowed down quite a bit, so you can see it better, but now you can see it's receiving bits and sending and receiving voltages. And then this is assuming full robustness of the bus. I'll talk about that limitation in a second. And essentially the same thing, except based off of that real-world flight data that I showed you from that flight path from earlier. So I'm not going to show you an attack, and I'm not going to show you the IDS turned on quite yet. I just want to show you first It is sending around 430,000 words, and then this is just on a couple of LRUs on the bus. So again, it would be much larger for just even an 8-hour flight that this is. And it's running very fast, and you can see that it has some words there that pitch the plane up and down, and then each word is color-coded to the specific bus and the model that it is. So if and then you can also slow this down too if you want. Okay, and now you can kind of see it running a little bit slower. And now I will show you the attack. I'm going to turn that on. As soon as I set this breakpoint right here, I want to set the breakpoint so you can see what's going on. I'm going to rerun this with the attack, not slowed down without the IDS. And you can see it calculated more words because the attack will inject more words through the FMC. Okay, so here's the breakpoint for the attack, and this is where you're in Iranian airspace. So now we're sending the plane down, not necessarily crashing it, but sending it down so that they have to declare a mayday and land. And another thing to note about this one simulation is that it usually takes on the order of 10 to 20 seconds. Which is about 1,000 times faster than it actually is, because this is on flight data for 8 hours. And then I will show you with the IDS, it does slow it down to about 3 minutes. So I'm going to let it run and put the breakpoint back in so that we won't get stuck on the attack while I go over my next slides. Okay, so for evaluations, I showed you a little bit of the first one as part of the demo. That was my mega test code base where I test every single function of the simulation for correctness. So everything down to those voltages, to the simulated LRUs, to the bus simulation, to the IDS function. So every function has a couple to maybe 10 or more test functions on those. Next evaluation metric that I had was IDS robustness. So this is seeing how fast I can have the IDS run in sending and receiving words with it being accurate on getting those specific words correct. Not necessarily testing for if the rules can get them, but seeing if it can sample at half a microsecond, which is real world speed, and actually translate that to words correctly. Then there was IDS correctness. Now this is, will it alert on and log on the words that I want it to, and not alert and log on the words that I don't want it to. Finally, can it detect an attack? Basically, effectively let the flight crew know, hey, this is a cyber attack, as opposed to for flight Qantas 72, this is a hardware failure on the ARINC. And then the last evaluation metric that I added was, will this slow down your plane? Will it slow down the bus by adding a lot of time? And it will slow down the plane getting out of the runway by adding a lot of time for setup. So this is an example of one of my functions in my megatest. Multiply this across every other class and every other function in those classes, and you'll get the whole megatest space, which is probably around 5,000 lines long. And then this is the IDS robustness results. So I was able to incorporate feedback from my classmates and speed this quite up from what it was in previous weeks. Unfortunately, it's not quite there at the real world speed. I'll discuss more on limitations as to why. And then there is a bug where it's carrying over bits from the previous word into the next word, so that's why the correct bits are going down there. But it is getting within spitting distance there of the actual real world speed, and that is just translating voltages to words within real world speed. And then there was no difference from 0 rules in the IDS to 10 rules for correctness on this part. This is the IDS correctness, and you'll see here a couple different graphs of my second test where I had about 200 million words and then a very short and sweet rules file, and I want to see will it alert and log on the words that I wanted to, and I'm happy to say that it does. It did alert and log on the expected amount of words that I wanted to, and then you can see that it's kind of straight because I had very simple alerts that it wanted to alert on, like that it sent a GPS word, and then I had very specific words that it wanted to alert on, like the angle of attack is specifically negative 1.0123506 or something like that. And then you can see if you zoom in on the graph here, there is a difference between the number of logs and number of words in the orange and blue. My next metric, is just seeing can it detect attacks. And so you can see here, this is where the attack is in that previous main function that I just showed you. This is where the downward words are. And then going over to the cumulative graph, you can see that it's just alerts and not logs because I sent alerts. Hey, it's sending spurious downward dive words. And then my final evaluation is seeing across a variety of channel numbers, a variety of number of LRUs, and variety of rules, does that slow down the bus significantly? So it's a variable number of channels, 36 to 48, variable number of LRUs per channel. You can only have 21, one transceiver, 20 receivers, and then 1 to 500 rules for those channels. So over you fixing two of those variables, you can put graphs and see the rise in time over each one. So generally, yes. Setting up the IDS and alerting or logging on one word does add a little bit more time to the bus. You can see the alerting on one word here in the very thin orange, and then setting up the IDS in the blue. However, it's within the order of like 1/10 of a second for setup, and then under 100th of a second for alerting or logging. Here's another example with a different amount of channels and LRUs, and you can see it does, with the exception of some outliers, rise a little bit. Fixing the channels and the number of rules and the variabling the number of LRUs, you can see that also raises the time to set up, but not quite that much for the alerting or logging on one word. And then here's the cumulative. And then you can see the simulation here finished for the 8-hour flight. It took a little bit longer than previously, and it does alert on those downward dive words as part of the attack. So moving on to some limitations. My model is pretty simple for a real Boeing 787. It would have way more LRUs and channels than this has. This only has 4 channels and about 6 LRUs. Whereas a real Boeing 737 would have like 36 to 48 channels, and it would have probably around 10 to 40 LRUs. Python multi-threading was a limitation where, as part of the robustness of receiving words, it was unable to receive them at real time just because Python multi-threading is slower than other languages. Making sure that the operator training on creating rules is correct, otherwise you won't get what you want and you won't see attacks if you don't have the correct rules. In terms of the stoppaging the plane, it doesn't actually, stopping an attack, it doesn't actually stop an attack, it just lets you know. It doesn't fulfill all the Zero Trust tenets. That being said, it does move it closer to all of them. So, for example, it does help measure and monitor the integrity of or the security of all assets, but it doesn't help to measure and monitor the integrity. That is for the 5th tenet there. And then I wasn't able to access real world hardware just because of cost, so it's untested on real hardware. So that brings me to my future work and possible next steps. Expanding to have more LRUs. Recode it so that it can be closer to real life, recoding it in a faster language like Rust, expanding IDS functionality to have a condition chain. For example, if there are more than 100 of these words on this LRU and then 50 on another LRU, having a functionality for that. Another one would be creating an intrusion prevention system. So that would take the last integrity bit and flip it if it alerts in the middle of a word. Implementing our real hardware would be great, and collecting more real-world word data. I had real-world flight data, but not real-world word data. And then diversity a threat model. Are there entrances as opposed to like a vampire attack or the legacy software, like through the radio or something else? So in summary, I went over this, and then it will be available on GitHub pending approval from teachers. These are my references.